Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry. I'm Ashley Martini. As always, the goal of our seminar series is to bring the community together. This seminar is streamed live on the third Thursday of every month at 11 a.m. Eastern. They are also available to watch anytime on our YouTube channel. We've had an outstanding group of speakers so far as part of the seminar series, and again, I encourage you to check them out on the YouTube channel. We also have some great speakers planned for the upcoming months, and we hope that you will join us for all of them. A few quick thank yous. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students without whom the seminar would not happen, Katie Floyd and Ryan Kwok. Thank you again for participating, for being here. Please do follow us on the YouTube channel to see subsequent seminars. Finally, a few quick guidelines. Reminder that the webinar is being recorded. If you have any questions during the seminar, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar. Finally, last but not least, it's my pleasure to welcome today's seminar speaker, Dr. Ina Vollmer. Dr. Vollmer is an assistant professor in the Inorganic Chemistry and Catalysis group at Utrecht University. Vollmer studied process engineering at Hamburg University of Applied Science and chemical engineering at Massachusetts Institute of Technology. She completed her doctorate in heterogeneous catalysis at the Technical University of Delft in the Netherlands. After a postdoc on chemical recycling of plastic and natural degradation of plastics to nanoplastics at Utrecht University in the Netherlands, Vollmer became an assistant professor there in 2021. She is a faculty council member and on the board of the Institute of Sustainable and Circular Chemistry. She received a Veni and Excess grant from the Dutch Research Council in 2021 and an ERC starting grant in 2024. It's my pleasure to welcome Dr. Ina Vollmer to the Mechanochemistry discussions.
Hello, everyone. Welcome to this talk about our work on mechano-catalytic depolymerization of plastic waste. So what I want to do is I want to first talk about our motivation for this, and this includes the key challenges in chemical recycling. I will then talk about our work on mechanocatalysis to depolymerize plastic waste, and focus on the reaction mechanism of it all, especially involving the radicals here. And then I will talk a bit about the upscaling potential of this and how we want to get there by a predictive relationship that tells us how much yield we will get in relation to force and temperature applied. So for me, the personal motivation is really the plastic waste, whether it is ending up in the environment here where cows are steeped in plastic waste, or whether this is this example, which was particularly striking to me, where plastic waste is actually used such as like fuel to cook tofu, so like wood, instead they burn plastic waste. And this, of course, leads to quite toxic emissions, which accumulate in the ground. And if chicken eat that, then it gets also into the food chain. Or, of course, plastic waste can also end up in the ocean and form micro and nanoplastics, which can also end up in the food chain again. And so, unfortunately, nowadays, the question whether we can live without plastics has to be answered with no. And this is a problem because, for example, in the EU, only 13.5% of new plastics are actually made from recycled material. One of the reasons is that classical recycling or physical recycling, so melting and reshaping, which is what is done currently, leads to a lower quality product. And it can also not be used to create food contact materials. In the EU, there's a lot of regulation that foresees that we want to have more and more recycled content in food packaging and in single-use items. And so this basically also forces companies to think about new ways of recycling. And the proposed solution here is chemical recycling, but as you can see, that still has to take off. And the main idea here is to obtain back the constituent monomers of this polymer, this then in the gas or liquid phase, so it can be cleaned up, additives can be removed, and then these monomers can be used to make a polymer of a high quality again. And this works rather well for polymers with a heteroatom in the backbone. So this is kind of a weak link where you can break the polymers into its constituent monomers. And this is the case, for example, for polyethylene terephthalate or PET, which we know very well from drinking bottles. However, there are also polyolefins, polyethylene and polypropylene, which do not have such a weak link in their backbone, but just the same kind of carbon-carbon bond all along the chain of the polymer. And so there is no weak link where we can selectively break the polymer into its monomers. And so if we want to design new recycling methods, we also have to think about the plastic value chain. Right now, plastics are made from oil and gas. This is sent to the cracker where monomers are produced. These are then polymerized, and the polymers are sent to the compounder. They add additives and so on to make the final product, which reaches the consumer. And after a sorting process, right now, the plastic is mostly incinerated or landfilled. And the only recycling that we do at the moment is mostly mechanical or physical recycling, which cannot produce the high quality material, as I explained before. So then with polyethylene terephthalate, we can do solvolysis. And this yields back the monomers, so you can directly make a high quality polymer again. However, with polyolefins and also with polystyrene, you don't really have this weak link. So the only thing that you can do right now is provide a high temperature treatment and make a fuel-like product that has to be sent to the cracker again. And important here is that every step in this process requires a lot of energy. So ideally, we would find a process to make monomers out of polyethylene and polypropylene as well, because these make up more than 50% of the current polymer production globally. And so what happens if you do this high temperature treatment during pyrolysis? So you do that with exclusion of air and oxygen so that the plastic is not burning, but pyrolyzing instead. You get a product which is very mixed. So this is a 2D GCMS chromatogram, and every little blob in this graph is a different chemical species. So there are thousands of different molecules formed, and this is why this has to go to the chemical industry again to make monomers out of it again, and it cannot be used directly to make plastics. So the reason for that is that these carbon-carbon bonds require quite some energy to be broken. So there's this barrier that has to be overcome to be broken, to cleave these bonds. And this is why we need such high temperatures. But at these high temperatures, we can also not suppress these follow-up reactions of the cleaved polymer, because these activation energy barriers are also very easily overcome. And this is why we get such a mixed and invaluable product. Now, usually in the chemical industry, we use catalysis to lower these barriers and also to tune the product scope. But there's a very big issue with using heterogeneous catalysis for polymers. And heterogeneous catalysis are preferred not only because we are a heterogeneous catalysis group, but also because they can be recovered and because we need very high temperatures. So heterogeneous catalysis seems to be more resistant against high temperatures. And so what you see here is basically the problem that I mentioned, that we have problems contacting the polymer and the catalyst. So we took a video of this process of converting polymer over a catalyst, and you see here these white dots, which are the catalyst particles, and then on top you see this blob of polymer. And right now we are still below the melting point of these polymers, and the difference between the top and the bottom is that this is a high molecular weight polymers, the low molecular weight polymer, so a short chain. And this is a high molecular weight polymer, which is a very long chain. And so if we then go to the melting point of the polymer, you see at the top that these shorter chains, they are really melting and flowing into the catalyst bed. So here you have good contact between the polymer and the catalyst particles. While at the bottom, we see that this blob of plastic is becoming a little bit more round, but it is not flowing into the catalyst bed. So there's no contact or very little contact with the catalyst particles. And this continues upon heating up. The polymer at the bottom is just curling up more and more. And at some point, you see that the bottom of this blob is reacting with the catalyst particles, but only at a very small contact area. And so this whole thing is very inefficient. And you see conversion at a much higher temperature than if you have this more low molecular weight polymer. And unfortunately, this polymer at the top, you can buy at Sigma Aldrich. But if you have a waste item, you will most likely encounter this bottom polymer with the high molecular weight. And so it's not very easy to contact the solid catalyst and the polymer particles. So getting the polymer into contact with the catalyst is as difficult as mixing honey with sand because the polymer becomes very viscous when molten. And then there's the second problem, and that is that the active sites of the catalyst where the polymer would be converted are inside an intricate network of pores, while the polymer is entangled like spaghetti. So actually getting the polymer into contact with these active sites is as difficult as threading spaghetti into a sponge. And so to solve the problem of the high temperature and the uncontrolled reactions, what if we use force instead of heat? So in this way, we actually stretch the polymer bonds, which increases the initial state and energy of the polymer, and thus lowers the activation energy barrier that the polymer has to overcome to be cleaved, as you can see here. And because now we can actually use much lower temperatures, this was observed to happen even at minus 196 degrees Celsius, these follow-up reactions are actually not activated. And at these low temperatures, these activation barriers are much harder to overcome. So this way we can get some control over the products that we form. And so the way we apply the force is in a ball mill. And this is a small vessel that shakes back and forth. And you can see this vessel here where you can actually see inside. And so when the grinding spheres inside it collide with some polymer in between, then it will experience the force necessary to break these carbon-carbon bonds. So you can also see an image of the opened up vessel here with the grinding spheres made of zirconia and then the solid polymer. And this is what we actually put inside. And what we get out is then actually in the gas phase. And to obtain this gas phase, we need an inlet and an outlet to this vessel. So we send a stream of nitrogen through this vessel, and that elutes our products. And when I first tried this out, I was really excited because I had worked on thermal pyrolysis before, and I'd seen that if you get to 250 degrees or something, you slowly start to see some gas phase products. But with this, without any additional heating at room temperature, we could see gas phase products coming out of this ball mill. And this was really exciting and also a bit unexpected. So when we really optimize the conditions, we can also already convert around half of the solid plastic to gas phase products in 1 hour. And you can see that the different products, they are around 30 different ones, a little bit less. And this is, of course, in stark contrast to what we get from pyrolysis with thousands of different products obtained there. And because there's a significant amount of propene in this gas phase stream, it also could make sense to actually separate these different products and to obtain the monomer from this process directly. It's a little bit similar to a steam cracker output, actually. And so basically with this, while with polyolefins before we had the option of physical recycling and pyrolysis, now we could have this link to make the monomer that can directly be used for repolymerization, and we could skip the cracker step, which is very energy intensive, of course. So to dive a little bit deeper into this mechanochemical process, we can look at the propene flow over time. So this is what we measure on the online GC and what comes out of the reactor together with this stream of nitrogen. And when we turn off the ball mill, this stream of propene immediately stops. And when we start the milling again, then the propene flow also starts up again. And during this same time, we also measured the temperature, and it does increase a little bit because of the friction occurring inside the ball mill. However, when we switch off the shaking, then the temperature actually decreases much more slowly than the propene formation. And this is the first indication that we are not just looking at a thermal effect here, but actually a mechanochemical effect. And this is also visible from the fact that for the thermal conversion, we need temperatures around above 250 degrees, while in this case, we do not actually even exceed the melting point of the polymer seemingly, as we obtain still a powder that doesn't show much sign of melting. And the temperature, at least measured on the outside of the container, also does not exceed 40 degrees Celsius. And so we want to improve the production of propene, and for that we still want to use a catalyst. However, I said that with heterogeneous catalysts we have some issues in getting them into contact with the polymer. And in the ball mill we also have an additional problem, and that is if we would use the catalyst just as powder, we would need to get the powder catalyst, the polymer, and the grinding spheres at the same location at the same time. And so the idea was then to use mechanocatalysis and actually direct mechanocatalysis. So instead of adding powder to the ball mill, we directly functionalize the surface of the grinding spheres. And for example, we use a treatment with sulfuric acid. And the initial idea was to create Brunswick acid sites because we knew that those were active for thermal catalysis. And so to demonstrate that this really has a benefit, you see here just a polymer converted with commercial zirconia grinding spheres. So there's already some propene formed, which I normalized here to 1. And then we added both tungstated zirconia and sulfated zirconia powder to the ball mill. And you see that there's no increase in activity. However, when we actually functionalize the surface of the grinding spheres directly, we do see a marked increase in activity. And to the heterogeneous catalysis world, this seems maybe a little bit surprising because usually we try to increase the surface area of the catalyst as much as possible. And in this case, we actually have a 4 orders of magnitude lower surface area of these functionalized grinding spheres compared to the powder. And still the powder is not active, while the surface functionalized grinding spheres actually are. And this really has to do with the improved contact because the catalyst is right where the impact into the system, the energy impact into the system is the highest, and also where the polymer experiences the force. But of course, we also want to understand a bit more deeply what the mechanism behind this catalysis is. And the initial idea, as I said, was to just imitate thermal catalysis and just to improve the contact between the polymer and the active site. And so in thermal catalysis, we have a Brunzit or a loose acid site, which then creates a carbocation intermediate on the polymer. And this can then further react to release small hydrocarbons. So how you can test the thermocatalysis is by using thermogravimetric analysis. And what you do is you put the polymer and the catalyst into a very small bucket and you weigh this bucket and then heat it up under nitrogen. And at a certain temperature, the weight will decrease because carbon-carbon bonds are broken. You form smaller molecules which evaporate, and thereby the weight decreases. And this is the curve you can see here. And so if we just use polypropylene at around 270 degrees, or at least above 450, you really see the highest weight loss. And if we just use the unfunctionalized zirconia grinding spheres, you also see that there's no change in this temperature. However, when we treat the commercial zirconia grinding spheres at 650 degrees with sulfuric acid, we see that the temperature decreases quite significantly. So there is a catalytic effect of these grinding spheres. And so then we used also another treatment at 800 degrees with the sulfuric acid, and this actually created absolutely no thermocatalytic activity. However, when we then use this in ball milling, which is what is shown here, you can see that the propene flow is a bit higher for this catalyst treated at 650 degrees, but it is even higher for the one treated at 800 degrees, which was not thermocatalytically active. So somehow there is a mismatch between what we see in thermocatalysis and what we see in mechanocatalysis. And because this active site, this Burns active site, is related to the sulfate groups, we also measured the amount of sulfate groups on these grinding spheres with Raman spectroscopy. And there you can also see that, as we would expect, the good thermocatalysis, the one treated at 650 degrees, shows a high amount of sulfate groups, while the one that is thermocatalytically inactive shows no sulfate groups. So we would also expect that there's little Brunzit acidity on that catalyst. So there seems to be something else that we are forming that actually causes the mechanocatalysis. So what we then speculated was that in mechanochemistry, we know that the carbon-carbon bonds actually break homolytically. So we would form radicals, as you can see here. And somehow we thought maybe our catalyst can interact with these radicals. It can either accelerate the initiation, or it can do something else. And so we tested whether we get more radicals when we add the catalytic grinding spheres, so whether the catalyst actually helps with the radical initiation. And this was work that a postdoc in our group did, and she used BHT, which has this OH group here, which easily gives off this hydrogen to the radical, and thereby the radical is actually terminated, and we create this very stable radical. And so when she added this BHT to the milling, we could actually see that without the BHT, we see the propene, but with the BHT, we suppress the propene formation entirely. And so this indicates that indeed, at some point in the mechanism, there has to be something with radicals. And then we further tested whether it is indeed the radical initiation, or whether the radicals are somehow stabilized and this formation of smaller hydrocarbons is promoted. And so for that, we looked at the GBC curves. So this is the molecular weight distribution before the milling. So this is in green without any milling. And then we milled for 10 hours and for 60 hours. And you can see the solid lines are without the catalyst, and the dashed lines are with the catalyst. And because the molecular weight is changing, so we see a lower molecular weight because we have the carbon-carbon bond cleavage. However, we don't see more cleavage when we add the catalyst. So this to us indicated that we are not seeing more initiation of the radicals, but actually we have to look at the second part. So we're not looking at the radical initiation, but we are looking maybe at the radical stabilization. And so what can stabilize radicals? Something redox active. So we tested with electron paramagnetic resonance spectroscopy whether we have unpaired electrons on our catalyst that could somehow interact with radicals. And as you can see here, the one that was thermocatalytically active showed no unpaired electrons, or at least below the detection limit, while the one treated at the higher temperature that was mechanochemically active or mechanocatalytically active, that showed a very high amount of these unpaired electrons. And then we actually went on to ask our colleagues to see whether they can look with DFT if these species that we speculate we have there, so that we observed actually, so the oxygen vacancy here and the zirconium 3+, which are both unpaired electrons, whether they can stabilize the radicals. And indeed, we see that this is the case, while a zirconia surface that has no defects cannot stabilize these radicals. And this is then very much in line with the mechanocatalytic activity that we observe. And we then also tried another material, which is this tungstated zirconia. And there you can create two different materials by either reducing the material, and then you have a lot of unpaired electrons with this tungsten 5+, and also zirconium 3+ increases in intensity, while just the prepared and calcined materials doesn't have that many unpaired electrons. And here we also see the difference in the stabilization of the radicals of the two materials. And so with that, I would like to move on to the reaction mechanism involving radicals. So how exactly does the radical stabilization help in the propene formation? So this radical mechanism was basically inspired from radical depolymerization mechanisms that were studied already a lot in the past and where we know quite a bit about. So the only difference here is that the initiation is at the formation of the radicals by mechanochemical force. So we have the homolytic carbon-carbon bond cleavage generating two radicals, and these can either terminate by recombining back and just reforming the polymer, or they can disproportionate by forming a saturated and an unsaturated bond. But what we really want, of course, is the depolymerization, which creates a monomer and also regenerates the radical. And there are also some other reactions that can happen, but we are focusing on the depolymerization here, of course. So if we want to promote the depolymerization, we can apply a kinetic trick that is also very well known from radical polymerization. And the trick is that for the depolymerization, the rate depends on the radical concentration to the power of 1, while for the termination, it depends on the radical concentration to the power of 2. So if we decrease the radical concentration, we proportionally suppress the termination much more than the depolymerization, and thereby we can actually promote the depolymerization over the termination. And so, as I explained before, we think that with our catalyst, we can actually stabilize the radicals for a while. So this decreases the radical concentration in the system and thereby promotes the depolymerization and suppresses the termination reactions. And to study this mechanism a bit more, we actually had to measure this radical concentration in the reactor a bit better, and especially the initiation rate of the radicals. And again, we use this trick of putting BHT into the ball milling chamber, where this OH group gives off the hydrogen to terminate the radical. And what we can then actually observe is the loss of this OH group. So here you can see again, when milling with different times, we form propene. And if we do that with the BHT, we never see any propene because it is suppressed. And then at these different milling times, we recover the material and we actually observe with infrared spectroscopy this OH group. And as you can see, with increased milling time, more and more of these OH groups have given off a hydrogen to the radical. And so this intensity decreases of the OH group. And we can actually then plot this over time. So this is the black dots here. And we convert this then to an OH concentration in the system. And at the same time, so this then tells us the initiation rates. And at the same time, we can also look at the rate of monomer formation from just the flow of propene coming out of the reactor. And this is shown here in the pink line. So this is then the depolymerization rate. And here we then try to compare the depolymerization to the termination. So we look at the competition between these two reactions by looking at reaction rate constants, so these Ks from literature. And what we assume here is that we are actually in steady state, so that the radical concentration in the system is always the same. So the radical concentration will be the initiation minus the termination. And if we set this to 0, then we can actually derive the monomer formation. So radical concentration as a function of the initiation rate, this KIP, and the termination rate constant that we got from literature. And then the monomer formation rate is this, which is also dependent on the reaction rate constant for the depolymerization. So just from getting literature reaction rate constants, we can now see whether this matches with our values that we obtained in the ball mill. And so in experiments, we observe this initiation rates, and this we can plug in here. And if we then plug in the reaction rate constants from literature, we actually get this depolymerization rate or monomer formation rate. And if we then compare that with our experiment, we see that actually, if we use the literature reaction rate constants, we would actually expect a much lower monomer formation rate than what we observe in the experiment. And this is very interesting because it can tell us a bit about what is actually happening in the ball mill. So what could happen is that in a very mixed reactor in solution, looking at radical polymerization, you would actually have the possibility of these radicals to recombine because the system is very well mixed. However, because these grinding spheres are hitting each other, they can actually displace the radicals and move them away from each other very efficiently. And this could effectively suppress the radical termination reactions. So this could be an effect. This could be the effect that we're observing here, and that would mean that we are actually seeing more depolymerization rather than recombination in our system already. And as I said before, we can also stabilize these radicals further with the activation of the surface of the grinding spheres, and thereby promote the monomer formation even further. An alternative explanation could, of course, be that we actually have a different temperature that we measured in the system, which would also increase the depolymerization rate over the termination rate. And when we calculated that, we found that instead of the 40 degrees, we could calculate 140 degrees, and this would then also explain our observed kinetics. But I just wanted to demonstrate that this gives us nice tools to study what is happening in the ball mill. So with that, I would like to move a bit into the future and look at upscaling. And so with the state of the art, as I explained, the vision is that we can improve this process. So with the state of the art for polyolefin conversion, we have to work at very high temperatures, which leads to very unselective reaction with a lot of mixed product that then has to also be cleaned up, because usually plastic waste has impurities, and then it can be sent to the steam cracker. And after that, it still needs to be separated to obtain the monomers. And with this, the whole efficiency of the process is only around 50% because of all the fuel that we have to burn to power these processes. And then with our process, the vision really would be that we can drive the ball mill at least electrically, or even use mechanical energy directly from wind or hydropower. And then, as I said, we can produce something that already looks similar to the steam cracker output. And so we would only need this separation, and maybe this ball mill could even be next to steam cracker and be separated. The product could be separated together with the steam cracker output. So this is in line with the electrification efforts of the chemical industry. However, we are working on a gram and sometimes even milligram scale, and we have this shaker geometry. And there's a lot of there are a lot of studies where it was tried to scale up these technologies and also move to other ball mill geometries, and it was found that this is very difficult. But a rotary system would actually be quite preferred, because there's quite some experience in the cement industry, for example, where they use these man-high ball mills. So it would be nice to know how we can translate this system to this large-scale system. And in the chemical industry, of course, usually we have some sort of kinetic relationship for that. We know if we increase the temperature by this much, the reaction rate increases by this much. And of course, there are many very nice examples of mechanochemistry out there, and we can really do other chemistry. We can drive synthesis. We can even drive gas phase reactions. And there's a lot of attempts to explain how the force that we put into the system leads to the chemical reaction. But it is still very difficult to get one coherent explanation. And so one explanation that is often used is the dose of kinetic energy. So this is the formula. So you have the kinetic energy times the number of collisions in a certain time frame, and then times the time. And the kinetic energy is then the mass times the velocity squared divided by 2. And the number of collisions we also need to calculate this. And so what we then tried is to do that for our experiments. And in this case, the kinetic energy is mostly dependent on the mass of the balls and the velocity. And this velocity actually is related to the frequency of the milling, so the shaking frequency. And so this is proportional to the frequency squared, the kinetic energy. And the number of collisions is also proportional to the frequency of milling directly. So that means that this dose of kinetic energy should be proportional to the milling frequency to the power of 3. And so this has also been done to explain the yield. And for PET conversion, so polyethylene terephthalate, which is this reaction where you use sodium hydroxide to then create this salt and ethylene glycol. this could actually be used to nicely explain the data with different milling frequencies. So on the x-axis, you see times the milling frequency to the power 3, and on the y-axis, the conversion of PET, and this looks very linear. However, in this process, the most important step is to mix the sodium hydroxide with the polymer, so to get this contact right. And in our case, we are looking at a little bit of a different mechanism. So when we try to we milled at different frequencies and looked at the yields of different products. And you can already see that, yeah, it could be linear, but it already does not look fully linear with the milling frequency. And then we tried to see how the yield behaves in relation to the milling frequency. And as you can see here, the yield is actually proportional to the milling frequency to the power of 5 or more. So it is not actually how we would expect it to behave if this would just be a linear relation with the dose of kinetic energy. And so we also did something similar with changing the density of the grinding spheres. So you can see here that, there are some materials which have a very low density, such as steel, zirconia, and alumina. And tungsten carbide, of course, has a very high density. And then if you plot this with the sphere density on the x-axis and the depolymerization rate on the y-axis, you can see that this also does not really look linear. But that's actually what you would expect, because the kinetic energy is directly proportional to the density, as you can see here. And so also here, the dose of kinetic energy approach does not seem to work very well. And so then in the beginning, I explained this concept of lowering the activation energy barrier by increasing the energy of the initial state by basically stretching the bonds of the polymer. And this is described what I call the Zorkov relationship, because there's a paper by Zorkov where he first describes this, but there are also other papers from other authors that developed something very similar. And with this, you can describe this lowering of the activation energy barrier by this term C sigma. And C is just an empirical constant that I will talk a bit more about later. But sigma really relates to the energy of the balls, or the force that you apply. And so what we need for that first is to get this K. So we, with the steady state approximation that I also explained earlier, we can calculate that the rate of monomer formation squared is this rate of radical formation, which is actually what we describe here. So the carbon-carbon bond cleavage to the radicals here on this side. And so if we plot this radical initiation rate on the y-axis and the milling frequency on the x-axis, we get this relationship. And then we need to have a description of the sigma, so the stress on the polymer. And this we describe by the impact force, so the mass of the spheres times the acceleration, and the impact area. And to calculate the impact area is a little bit more tricky, because you need to know how deeply the sphere actually goes into the polymer material upon impact. And this we calculate from Hertz theory that I will not explain in too much detail here. But basically what this yields us is this stress, as there's a function of the stress, which is actually dependent on the milling frequencies to the power of 2/3. And so this whole term, we do not change in this experiment, just the frequency. And so this is the constant times RT, as you can see here. And this is then the formula that we used for fitting this data. And so part of it is the activation energy barrier of the thermal part of the reaction, so this EA, plus the pre-exponential factor, and we just combine this into a constant for fitting because we are not changing the temperature in these experiments. And then we also have to include something about the number of collisions that we also increase with the milling frequency. And as you can see here, this formula can actually fit this data quite well. And we can then obtain this factor C, this empirical constant. And we try to do the same then. But what about this empirical constant? So this is basically an activation volume, it is often called, and it has to do with how well the force that is applied on a macroscopic piece of polymer actually arrives at the polymer bond. So if we have this entangled material with all these different polymers here in different colors, and we basically hit this from the top, then there are a lot of properties of the polymer which can actually influence how well this force arrives at single bonds. So there can be different, there can be a different crystallinity degree, but there can also be different crystal sizes. So you can see here polymer that is very ordered. So these are crystals, and then in between you have more loosely entangled polymers, or also the degree on which how spaghetti-like the material is in the amorphous region, so how entangled and intertwined the polymers are, can also influence how the force is transferred through the macroscopic piece of polymer. And so we also applied this fitting to the experiments with the different densities. And we also get a C value here. And as you can see, they are actually surprisingly close, although not the same, for changing the frequency and changing the density. And when we look at the papers of Surkov that this model is taken from, then he obtained, of course, quite a different value for C, which is an order of magnitude lower. But this is also because he actually used tensile testing, where this can also be expected to be quite different. Okay, so with that, a question that we often get is, so what is this process actually applicable to? So we have tried high molecular weight polypropylene and low molecular weight polypropylene. We've tried a waste item of polypropylene from this blueberry cup, and we've also tried polyethylene, and even this industrial waste, which also contains contamination of other polymers, so polyamides, PET, EVOH, and polystyrene. And in all these cases, you can see that these grinding spheres, which were catalytically activated, show a much improved performance over the commercial zirconia grinding spheres. And this is particularly striking for this industrial waste sample. And for polystyrene, this depolymerization is generally not as challenging because it depolymerizes more easily also under thermal conditions. But also in this case, we could see that our catalyst has some advantages. And we hope that with our process, we would also have less reactor corrosion because we are working at such low temperatures, and we might form hydrochloric acid from PVC contaminations, but they might not be as corrosive because of the low temperatures that we apply. And to how long can we use these grinding spheres? So indeed, because this is a rough process, there is attrition and rubbing off of the activated surface of these grinding spheres over time. We see here that with the red and blue curves of the catalytic materials, they are inactive after some time. Then they approach the same activity as without the catalytic functionalization. But we can easily regenerate this material just with a simple sulfuric acid treatment, and then we can also reuse these materials over several cycles. And with that, I want to thank a couple of people. So PhD Adrian Hergesell and postdoc Claire Seitzinger mostly, and a couple of master and bachelor students that worked on this, as well as the plastic team and our collaborators, and of course the funding agency, so mostly the Dutch Research Council and also the Advanced ARCCBC. And I want to thank you, of course, for the attention, and I hope there are some interesting questions as well. Thank you.
All right, thank you for your presentation. We have a few questions from the audience. First, how generalizable are the results that you've shown with zirconia to other materials?
So we have, of course, tried to get this more encompassing relationship with this kinetic relationships based on the Zorkov model. So we have tried here several materials, and it seems that if we just look at the mechanochemistry itself, then the density of the grinding sphere seems to be most important in looking at the activity. And so that could also be a hint at this designing other materials in the future, because we could have, of course, another core than the catalytic functionalization that we use.
All right, thank you. Another question about the zirconia. Did you observe a surface wear from your functionalized zirconia catalysts? And how do you know the sulfuric acid is staying bound to the zirconia and not just acting as a lag agent?
Yeah, so we have actually tried milling also just with sulfuric acid. And in that case, we do not see any activity of the material. So any improved activity. Actually, sulfuric acid just added as a liquid to the reaction does more or less suppress the reaction. And so this high temperature treatment does, of course, create these sulfate groups, and they stay on there for a while. But as I explained later on, these actually are not what is most active in the catalysis. So actually, this etching with the sulfuric acid is creating some surface roughness, which can also play a role, but most importantly, it creates these oxygen defects, and together with zirconium 3+, which can actually stabilize the radicals.
Got it. Thank you. All right, another question, shifting gears a little bit. Are there any techno-economic studies for this process?
No, there are no techno-economic studies yet, but this is definitely the plan for the future.
Great. All right, so we have lots of questions. I'll try to squeeze in a couple more here. All right, in the calculations, you show that surface defects play a key role. Is there any way to evaluate this experimentally?
Yeah, so of course we did already try to do that by creating two different materials, one with less defects and one with more defects, as you can see here. So we have the sulfated zirconia treated at 650 degrees Celsius and the one treated at 800 here in the darker color. And we can see that this material that does not show many defects is also not mechanocatalytically active. But we are also thinking about some in situ experiments where we could generate the radicals somehow in the EPR, so in the electroparamagnetic resonance instrument, so that we could then see if we can generate the organic radicals and have next to it this these unpaired electrons on our catalyst, and then see if these actually disappear. The signal for that it disappears when the radicals then come to the catalyst material. That would of course be the ultimate proof, but so far we are mostly playing with different catalyst materials and try to draw some correlations between activity and material characterization.
Great. All right, we have so many questions, but I'm going to choose just two more for you. Here's one, perhaps a simple one. Great presentation. I'm wondering how easy it is to functionalize the zirconia.
Yeah, so there are different possibilities, of course. Some of them are a bit easier, some of them are more difficult, but this sulfuric acid treatment is just really just putting the spheres into sulfuric acid, concentrate it, and then just put it in the oven, heat it up to 650 or 800 degrees, and then you have your material.
All right. Okay. This is the last one. I'll be here, maybe overlapping a bit, but we'll ask is how is the abrasion? Is the surface active site stable during a long-term test?
Yeah, I tried to show this already a bit in the very end, because this is, of course, a very important question. So this was this slide. You can see that after a few hours, it does. So after around 5 hours, the surface likely completely rubbed off. And we also have SEM images of that. And we see that the surface was quite rough before the experiment, and then after the experiment it becomes more smooth. So we definitely need to find a way to have spheres that regenerate the active surface upon milling. And of course you could think about bulk treatments that generate defects in the bulk of the material. So if we just rub off a little bit, then we just have a new surface that can act as a catalyst.
All right, excellent. Thank you again for your presentation.
Thank you.
Thank you, Dr. Vollmer, for that outstanding presentation. And thank you so much for joining us. Just a reminder that we've had a great group of speakers as part of the seminar series, and you can watch all of them on the YouTube channel. We also have a great group of speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.